Okay, welcome to the classification in data mining. Hope you have gone through the slide set and the short video that I have shared. So in this session, I'll be walk through the classification techniques or the concepts through a tool. Tool is WEKA. WEKA is developed by Waikato University in New Zealand. Uh, so before we move into the WEKA tool, let me first explain what the classification is just to start this session. So classification is you are classifying, we call it a supervised learning technique. That is, we will have some label data and some independent attributes. For example, let me go to the classical example that most of the classification the classes are using, that is the Irish flower. So if you look at Irish flower, there are 4 parameters that defines the type of the Irish flower: petal length, petal width, sepal length, and sepal width. Depending on those 4 parameters, it will define whether the Irish flower falls into which category out of given 3. So we should have label data. We should have label data when performing classifications. So make sure when you are doing a classification, if your problem is classification, you need to have label data. If not, you have to do labeling, or it can be manual annotation. Manually you can label those data, or else using some tools like LLM or whatever, you can label the data. So to start with, you will have to have label data when you are doing classification. Next question is, what is the classification process? So we should have the collected data, which is, as I said, those should be labeled data. Then we do data pre-processing. Sometimes you will have missing values, sometimes you will have outliers, or sometimes you will have unnecessary columns, rows. So you have to remove them or replace outliers depending on the case that you are using it. Then the feature selection and feature engineering. So feature selection is out of so sometimes when you are working with data, you will get 100 plus attributes. You might not need all those features. We are not going to discuss about the feature selection and feature engineering techniques here, but you need to understand, before we do anything, we need to have to start with the feature selection and feature engineering techniques as well. So once you are ready with your data set, then you are starting the classification process. So you can split your data into training, validation, and testing. In some cases, it is just the training and testing. Most tools supports training, validation, and training and testing. Some tools supports training, validation, and testing. Then you train your model using different algorithms. It can be decision trees, naive Bayes, SVM, so on and so forth. And then we'll validate the model, how accurate our model is. Remember, in classification, what we are going to do is we are going to predict. So someone, when you build a model, someone needs to accept your model. Now, for the acceptance of the end users, you need to tell what are the model validation, the parameters, evaluation parameters. So once you have selected the model, then you can do the final model testing and you can deploy and ready for prediction. So that's a basic process of processing the classification. Right. So before me moving into the slides, now let's go back to the WEKA tool. So this is the tool. Its version I'm using is 3.9.5. 3.8 version is also okay. You can see it's developed by the University of Waikato. This is the bird endemic to New Zealand. And this tool, I would say at the start, not a very cooperative tool or very user-friendly tool, but it can explain a lot of data mining or classification, data mining concepts from this tool. So for today, I'll be using the Explorer, and then I will select a data set. So here you can select the data set. You can select any data set out of these types. So you can have the ARFF, which is the most memory optimized data file for the WEKA. and then you have the JSON files, CSV files, and lot other files. So what I will do is I will go and select the files where WEKA has given us some sample files. So these are the sample files that WEKA has provided with its installation. So I'll be, for this particular session, I'll be using two data sets. So I will use the diabetics data sets. Right. So here, if you look at this data set, you can see I have 768 instance of records. So if I want to see the data, I can see the data from here. So these parameters, I'm not sure these are medical parameters. Only thing I know is the mass and the age, and then the class, whether you are tested positive for diabetics or tested negative for diabetics. So these are the 700 plus records that are available in the given data set. If you want to remove data, you can do that. If you want to add any instances, you can do that in WEKA, which I'm not going to do right now. And if you go to the WEKA, you will see the classes. So you can see there are 500 negative cases and 268 positive cases. So altogether 768 cases. If you want the distribution, let's say the age-wise distribution. So this will explain. So you can see the between 21 to some value you can see. So this distribution is tested negative or positive. So you may have remember the blue one is a negative, red one is a positive one. So here at this age, you can see the majority of them are negative. At this age, you can see the 50 per 50 negative and positive cases. So that's how you can see the distribution. You can see the distribution of other parameters as well to get an understanding about your data set. Right. So then next task is to classify. So here, if you go to classify, there are different classification techniques that are available. So there are a lot of classification techniques. To be very honest with you, I haven't seen this many algorithms in other tools. That's the one reason that I'm using WEKA to demonstrate the features. So let me select this very simple algorithm, naive Bayes. I'm not going to discuss about the algorithm, how it works, right? I'm just going to discuss about just the parameter that I am using. So now you can see there are four options. There are four options for us to select the test this mechanism. So before we move into that, let's go back and see what are these uh, the testing process. So this is what we do in classification. Let me take this example first. Uh, okay. So when it comes to classification, this is what we do. I'll take this as the first example since we are working on the diabetic data set. So let's assume we have 150 samples. We divide them into two sets, training and testing. And then using the training data set, we will build the model. Using the testing data set, we will validate whether this model is correct. Now, for example, let's say we have 150 records. Out of this 150 record, 105 records will be used to train the model. So then we have a model. So by choosing different parameters, let's say we have a model built on decision trees. And now how to validate this? So we have 45 samples data in test instance to validate this. So when it comes to diabetic data, 45 records we have those 6 or 7 parameters, and it says whether that particular patient is diabetic positive or negative. We will ask model to predict what the model think, whether it's a positive or a negative case. Now we have the predicted value and we have the actual value. From those, we will be verifying how much accurate data that it was predicted. So this was the simplest example for diabetic dataset. So this one is the most the little complex. So you can see there are three classes here. There are three class, the values are here. Here we have only two class values. And here we are using the training, testing, and training, validation, and testing only. So most of the time, when it comes to small dataset, we are just using training and testing instances. So now we have selected the diabetic dataset, and then we are going to classify. So we have few options here, but for the moment I'll be using the percentage split. So basically on percentage we are splitting the training dataset and the testing dataset. Then you might ask, okay, what is the percentage? It depends. Typically we go for 70 and 30. There are instances where we go for 80-20 as well, but in that range, 70 to 80 range would be our training dataset. Now remember one thing. If you have very small data set, as soon as you divide your data into training data set, you are reducing your data volume. If you have 150 records, if you go by the 80-20 rule, then you will end up with 120 records to build the model. Balance 30 will be used for testing. So whenever you use splitting option, remember you are reducing your data volume. So I'll explain two more test options here. One is using the same dataset. So training and testing will be done by the same dataset. You do the training from the dataset and you use the same dataset to test the model, which is not recommended. You obviously know that it is you're asking the same person about what he thinks which he was used to train. Then you can supply a different dataset for testing. That is also sort of not recommended because it can have a different context. For example, your training dataset is collected in 2025 and your testing dataset is 2020. So it doesn't have the same context, right? So you need to make sure you are testing using the same context as well. So the percentage split is the most common option that people use. So I will choose 80 records, 80 percentage. 80% of data for the training dataset. There are a few options which I'm not going to discuss here. And then you can see by default, it has selected the class variable. Now, so in the dataset, it has selected the class variable. If it is not, you have to pick and choose the dataset. Okay, now let's run this. Okay. So just to look at few numbers, let me go to the calculator. Right. So we had 768 records. We had 768 records, out of which we are using 30. We are using 80% for test training and 20% for testing. So if I multiply this by 20%, we will have roughly around 154 records for testing. And if you add these two numbers, 119 and 35, so that means that this is that 154 records. So basically what this says is we have 768 records. We divided them into 80 and 20. 80% of data was used to train the model. Balance the 20%, which is 150 records, were used to test the model. Now, what does this split means? So now, if you look at the data set, right? So we have few parameters, parameter 2, parameter 3, and we have the mass, age, and few more parameters. I can't remember those parameters. And then the positive or negative, positive or negative, right? So now, so these may have values, some values. I'm just including that, and then it says positive, right? So you will have similar values for another, right? You will have similar values for 100, all the 154 records like this, and it says some values, it says negative, and it might say positive. So these are labeled data. You don't know, these are the actual values. These are the actual values, right? So this is actual. Then what you do is, you pass these parameters to the build model. Now you have a model. You will asking from the model, what do you think? So this will be the predicted positive or negative. Let's assume this says positive. So this is actual value is positive and predicted value is positive. So this is correct prediction. Actual value is negative, but you predicted positive. So this one is wrong. This one is positive, and let's assume you have predicted it correctly as well. So then it is correct. This one is positive. Let's assume your model predicted it as positive. So then it's again correct. Now out of 4 records, 3 were correct. That means 3 divided by 4, you are into 75% of accuracy. So if I go back to this, right, we have 154 records. We have 154 records. Out of the 154 records, 119 records were correct. And 35 is wrong. So if we calculate the accuracy, 119 divided by 154, which is 77%, 2.7. Right? That's how you calculate the accuracy. Then the question is accuracy enough? Especially when you have imbalanced data. What do you mean by imbalanced data? If I go back to my data set, here you will say you have 768 records, 500 of them are negative and 268 of them are positive. So you don't have a balanced data. So since you don't have balanced data, when predicting, if you're going only by the accuracy, it might not be correct. This is a typical case in medical data. If you are using medical research, the data analytics, you will end up with data where you don't have imbalanced data. It's hard to get in balanced data in medical environment. Fraud, same. You will not get 50-50 class distribution. Right. Now let's go back and think about this model. What is the idea of a diabetic model? We want to identify positive diabetic cases. Keep that in mind. So then the important thing is this confusion matrix. I have included them in the slide, the false negative, false positive, but let's don't by heart that. Let's see what this confusion matrix tells us. Right. So you can see this 89. So this classified as means predicted. This is the actual. So this 89 means actually there are 89 negative uh, negative cases, and you have predicted them as negative as well. A is negative. So this side, you can see this side is the actual, this side is the predicted. So 89 means there are tested negative case, there are 89 negative cases and they have predicted as negative. So no issues. And there are 30 cases, and they are positive and predicted as positive. If you add these two numbers, 89 and 30, which are the correct predictions? 89 again, negative cases, and they are predicted as negative. 30, they are positive 30 cases, and they are predicted as 30. If you add this 89 to 30, that is 190. So this should match. 89 and 30 means this 119. This should match. Then look at the errors. This 16 means they are negative, but they were predicted as positive. Then this 19 means they are positive, but predicted as negative. If you add those two, 19 plus 16, you will end up with 35, which is this. So confusion matrix is a detailed analysis of your accuracy. Yes, those both are incorrect numbers. 19 and 16 both are incorrect, which is 35. But it tells you more detail about this 30, 35, and more details about this 190. Right. Now, out of this 19 and 16, what is the most significant error? Are both same? Or is there a significant error out of these two? Think about the case. There are positive cases, they are actually positive cases identified as negative. There are negative cases identified as positive. So again, no, think not limiting this to a technical aspect. Both are errors, yes, true. We have to minimize the both errors, yes, true. But again, why we have built this model? If you are building a diabetic model, we want to identify the patients. So our prime target would be identify the positive cases. So therefore, I would say this our model is targeting identify the positive cases, therefore label them as negative, which is this 19 is the most significant error out of this entire 35. Again, we are building a model to identify the positive diabetic cases. That's our rationale of that's our mandate for this particular model. So if there are the cases where they have labeled as negative, that is more significant, not the other one. There are 16 negative cases which are identified as positive. That's an error. I have no issue. That's an error also. But the 19 is the most significant error. So therefore, most of the cases, we don't stop at accuracy. Accuracy is an indication, but it doesn't give you the correct picture about your model. Right. So now let's dig into more details about this. So we are targeting the tested positive the site. So we are looking into this. So our focus should be on this. Right. So we are interested in these 4 parameters: precision, recall, F measure, and the MCC value. Right. So our focus is on positive cases. Right. Precision means precision and recall. Don't buy hard this. Right. This is how you find the difference between the precision and recall. Precision means out of predicted, how many of them are correct? out of predicted, how many of them are correct. Recall means out of actuals, how many of them are predicted. It sounds similar, but it gives you a different meanings altogether. Again, precision is out of predicted, how many of them are correct. Let's go and verify that from this particular uh, confusion matrix, right? So we are looking at positive. Our focus is positive. Out of predicted. So we are looking at this side. This is the prediction side, right? So we in this model has predicted 46 positive cases. This model has predicted 46 positive cases, out of which 30 is correct. This model has predicted 46 positive cases, out of which 30 is correct. Let me go back to the calculator. So we have 30 correct instances out of 46 predicted, right? So our precision value is 65.21, which is what you are seeing here, 65.2 something, right? So out of predicted, how many of them are correctly, how many of them are correct? Now let's go to the recall. Recall means out of actual, how many of you have predicted? If I relate to this case, out of positive diabetic patients, how many of you predicted them correctly? Right. So then out of positive diabetic cases, which means actual. So we are looking at this side. We are looking at this side. So we have 49 cases and we have predicted 30 of them correctly. So let me go back to the calculator. So we have 30 out of 49, which is the value is 61.2 or 0.612. So that is our recall value. That is our recall value. Now you can see even your accuracy is 77%, which is very good. Your precision and recall values are not very good. Right? Yes, the negative cases, precision and recall is very good. But our focus here is to identify the positive cases, not about the negative cases. Right? So typically in medical examples, we look at the recall value. Out of actuals, how many of them we can predict. Fraud cases, we are looking at the recall. Right. F1 measure is basically the harmonic mean of precision and recall. So I'm not going to discuss how you calculate it. There is a special calculation for harmonic mean. You can go through the extra reading and find it out. Simple calculation. And there are in Excel formulas are also available for harmonic mean. So you can find it out. That basically if you want to look at the both cases, precision and recall both, you would look at the F measure. Now you can see these three values, precision, recall, measure, it depends on the target variable. So if you are looking at the negative patients, you will be looking at the precision, recall, and F measure. F measure for these values. Positive cases, you are looking at these values. MCC, Matthews correlation coefficient, again little bit calculations are there. I have included them in the slides. So it is similar for whatever the class that you choose. Hope you understand how to identify the different evaluation models. Now here, so I have chosen naive base. Let me choose another uh, algorithm. Let me choose J48, which stand for decision trees. Right. So you can see, let me check the values here again. So the previous one's accuracy was 77%. This one accuracy is 65%. But recall has improved. You can see here the recall was 61% for the positive cases, but for decision tree, recall is slightly improved for 63%. So if I have a choice between the naive Bayes and decision trees, I would go for decision trees, even though it has lesser accuracy, but simply because it has a higher recall, I would go for decision tree because this particular the domain, medical domain. Let me choose another algorithm. Okay, you can see it has improved the accuracy, but it has a very poor recall. So I'm not looking at the accuracy here. I'm not looking at the accuracy alone. I'm looking at the recall for the positive cases. Let me choose another algorithm. So this is accuracy is also less, recall is also less. There are a lot of algorithms, but I'm not going to use them. Let me try this one. Okay, again, higher accuracy, but low recall values. So likewise, you have to choose between these methods and identify what is best suited for you. So this is a very poor uh, algorithm. Sorry. So likewise, you can try it out, the best algorithm that works for your dataset. Now, one thing to remember, depending on your dataset, you might have a different the parameter value. So you can't decide this is the algorithm and this is the parameter that you chose. It depends on your model, so you have to go back and check again and again. Right. So now let's go back to uh, the iris dataset. So iris dataset is a little different. It has three class variables: setosa, versicolor, and some other one. And it has balanced dataset, right? So what is this dataset? Setosa, versicolor, and virginica. And we have four different parameters. This is the petal, this is the sepal, and we have the petal length and the petal width. So we have the four variables: sepal length, sepal width, petal length, petal width. So this is the petal and this is the sepal, right? So this is the width, this is the width and the length, I would assume. So depending on those four parameters, we are going to define what is the flower class. So we will use the same algorithm, the same tool again. So we have iris flower dataset. So you can see those. So we can go and see the values here. So these are the values: sepal length, sepal width, petal length, petal width. And you can see here all 150 are equally distributed among three classes. This is a very lucky data set. You will not get this type of data set when you are working with the real data set. So again, I'll be using the percentage split. I'll use the uh, decision trees for this, or okay, let's use the decision trees for this and see. Right. So I have 150 records. When I have 150 records, 80% means 120. So I have 30 records to test my algorithm. So you can see here, all 30 data sets were predicted accurately. So no issues at all. That is where you will see precision is 100%, recall is 100%, F1 measure is 100%. And here you can see, if you look at the confusion matrix, all numbers are aligned on this diagonal, which means this 11, 10, 9, you add them up together, that will end up with 30, and all are correctly predicted. Let me choose a different algorithm just to see. Okay. So it's almost 100, 97% accuracy, and we have one invalidly uh, labeled or predicted instance. So if you look at this one, this means it is actually a Virginica and predicted as versicolor, predicted as B, which is the versicolor, right? So now you will understand how to identify or how to identify a classification model for your selected dataset, right? So don't just go by the accuracy. You have to look at the different other evaluation parameters, precision and recall mainly. So if I summarize what we discussed about classification using WEKA tool. So there what we did was we had the initial data set. It was divided among two, that is training and testing data set. So typically we use 80% 20% rule, or it can, depending on your data, you can go to 70-30, 75-25 likewise. So what we do is from the training data set, we build the model, and the rest test data is used to predict the verify your model. Those are the labeled data. So we will ask to model to give his thought about this data. Then we compare the actual value with the compared value. So to do that, we have a confusion matrix and the accuracy. So confusion matrix will give you the more details about your accuracy by accurately and the incorrectly valued data, incorrectly labeled data. And then we have two more parameters, that is recall and precision. Precision is out of predicted, how many of them are correct? Out of predicted, how many of them are correct? Recall means out of the existing data, how many of them were corrected, how many of them were correctly predicted. So remember those two terms, don't by heart them, look at the confusion matrix and try to understand that. Hope you get some sort of understanding into this. I'll be doing another video on using how to do the same thing from a different tool, which will be Orange Data Mining Tool. Hope you uh, understood this, the simple yet can be confusing the classification models. We will see you with another video.